All right, so for this clip note number 6, we're going to review the intermediate value theorem. And we have come to use the acronym IVT. So just to remind you, the intermediate value theorem can also be referred to as IVT. Totally acceptable in our work. All right, these are the 3 conditions that have to be true in order for us to use the IVT. And just notice that really kind of a main part of this is that the function is continuous. Okay. All right, use the IVT to show that this function has a 0, has an x-intercept between x equals 0 and x equals 1. So these are your x values. We've come to know these as a and b also. All right, so how do we show that we have a y value of 0 when x is 0 and x is 1? Well, let's just plug in each of these x values to the function. So let's evaluate the function at x equals 0. So 0, 0, that's negative 1. Let's plug in b to our function and get that y value. So we're creating 2 points. Okay, 1 plus 2 minus 1. The ones will cancel, that's 2. So notice these 2 points, when plotted, would give you a y value that falls below the x-axis and a y value that's above the x-axis. And there's no way on a continuous function, and this is continuous, okay, that you can go from a negative y to a positive y without passing through the x-axis, without passing through a y value of 0. All right, to show it, we're going to take the 0 that we're talking about and put it between these 2 other y values. So I can put negative 1 on the left and 2 on the right, but I'm going to look kind of smart here, and instead of putting negative 1 on the left, I'm going to put the function notation f of 0. And instead of putting 2 on the right, I'm going to put the function notation that represents f of 1 on the right. So 0 falls between negative 1 and 2. We just used the IVT to show that we have a 0 in the interval of x's between x equals 0 and x equals 1. So these are kind of the ways they test the IVT. Let's look at part 2, or question 2. All right, f is a twice differentiable function. That just means that it's capable of being differentiated twice. Okay, notice that you get 2 points that are on the f function. Okay, so far so good. All right, then it gives us another function h that's equal to f of x minus x. And let's just kind of pause here. If h is built from f and f is differentiable, then h is also differentiable. And remember, if h is differentiable, if anything's differentiable, differentiability implies continuity. So I can say that h is also continuous. And because we're talking about the IVT, that's the only condition we need to worry about is the continuity piece. But again, like I said, differentiability implies continuity. All right, they want us to use words, explain why there must be a value r between 2 and 5 such that I get a y value for that r. Okay, so we're talking about y values. So this probably is going to be the IVT, and it is because it's on this page. All right, so 0 has to be a y value that falls between the 2 y values when r is 2 and 5. So what we're going to do, because we're talking about the h function, is let's evaluate the h function at 2 and evaluate the h function at 5. So consider this your a value and your b value, your smallest x and your biggest x. All right, so h of 2, well, here's h, here's 2, that's the input, so it's going to be f of 2 minus 2. Everywhere you see x, replace it with 2. All right, f of 2 is given, it's 5. Just bring down the minus 2. All right, so this y value on the h function would be 3. So the 0.23 is on h. Let's do the 5. So h of 5 is equal to f of 5 minus 5. I'm just plugging in 5 everywhere I see x. F of 5 is given, that's 2. 2 minus 5 is negative 3. All right, does 0 fall between these 2 y values? Because these are the 2 points that are on this graph. Yeah, it does. So 0 falls between negative 3 on the left and positive 3 on the right. Well, again, like the last problem, I'm going to look kind of smart, and I'm going to put h of 5 here and h of 2 here. When it says explain, you might want to do a little more, throw in a few words there. Okay, if I'm using the IVT, the condition that has to be met is this. Since h of x is continuous, the IVT applies. And I could either rewrite this, or actually this time I'll probably just going to do the actual values here. So h of r must be equal to 0. All right, let's look at example 3. All right, so in example 1, we dealt with a function. Example 2, we dealt with the generic function. Notice example 3 is a data table. Okay, what's important is that f of x is continuous. Okay, these are your two x values. The endpoints, I guess, is consider that A, consider that B. Which of the following statements must be true? All right, so I have to have a y value of 5. Well, I'm looking for y values in my data table that are less than 5 and bigger than 5, and I can see that 5 would fit between these two y values. So yes, somewhere between the x values of -1 and 0, I have to pass through a y value of 5. That's true. And I might remind you at this point right here, strategy, a real good strategy is draw a continuous function having this left endpoint, that right endpoint, and all these points in between. Draw a picture. There are only 5 points. It's pretty manageable. All right, 2. Do I have to have a 0 between x equals -2 and -1? All right, well, here's x equals -2, here's x equals -1. Do I have to go through the x-axis? Yeah, because there's no way I can go from a -y to a positive y without passing through the x-axis. All right, a 0 of f of x is 6. And another way to say that is 6, 0 is an x-intercept. It doesn't have to be true. And besides, I don't have any data information about x values beyond 2. So I have definitely no information about this. So it doesn't have to be true. So at this point, I'm just going to say 1 and 2 have to be true. I'm going to choose choice D. Okay, so that wraps up the IVT. All right, so this cliff note is average rate of change, or as we've come to know that, AROC. Okay, we're going to make an addition here. You can see the change in y over the change in x is equal to, this notation is really instantaneous rate of change. So the average rate of change is equal to the instantaneous rate of change when we have a linear function. But typically the way you see delta y over delta x is a change in y's over a change in x's. You know it as y2 minus y1 over x2 minus x1. And that's what this video deals with. All right, example 1. Okay, we have a graph of bacteria growing over days, so we want to pay attention to the axis and the scale. We have 2 points that are on this graph. We're going to find the average rate of change from P to Q and draw on the secant line. Okay, well, drawing in the secant line, you guys can use a straight edge. It's not as easy as it looks here. Close enough. Pretty close. All right. So that's a graphical representation of the AROC. So let's find the AROC. From P to Q. So that's the change in y over change in x. You could use B for bacteria for the y's and D for days for the x's. You could have a change in B over a change in D if you wanted to. Now let's just go ahead and do y2 minus y1. So let's subtract the 2 y coordinates of the 2 points given. If you wanted to, you could put bacteria on top. And 45 minus 23. And this is days. Okay, and simplifying here, it looks like you're going to get 190 over 22. That would simplify because both those numbers are even. But again, we don't have to simplify. So this is the average rate of change on that time interval. If you were asked to interpret the meaning of your answer, I actually found an average rate of change, okay, and it's positive. So in the context of the problem, it just means that the bacteria is increasing at an average rate of, the number of bacteria is increasing at an average rate of, let's dump in the number we found, 190 over 22 bacteria per day. And this is on the time interval from day 3 to day 45. Okay, I think anytime we get a chance to practice interpretation of the meaning of our answer, we should take advantage of that. All right, example 2. So an equation to model the free fall of a ball drop from 30 feet high is, we've got a function to work with this time. What's the average rate of change for the first 3 minutes? So from t equals 0 to t equals 3, or in this case, x equals 0 to x equals 3, since x is the input. So let's find f of 0. That's easy. That's just 30. And let's plug in 3. When you do the computations here, you get negative 114. All right, what's the average rate of change? All right, the setup that's going to lead to our answer would be the change in the y values over the change in the x's. State units. Well, the output units are feet and the input units are minutes. This is going to be negative 144 over 3. This is going to simplify to negative 48 feet per minute. All right, let's look at example 3. All right, so in example 1, we dealt with a graph. We were finding average rate of change. Example 2, we were dealing with a function, finding average rate of change. Okay, notice that 3 is a little bit different. It says use the table. Now we're dealing with the table to estimate the instantaneous rate of change. That's what the prime means here in the year 1870. So if we're going to estimate it, that word typically means use an average rate of change to estimate the slope of the graph at the year 1870. Okay, so f prime, that instantaneous rate of change in the year 1870 is approximately, we'll have to use an average rate of change. I'm going to use the 2 points on either side of the year 1870. It'd be okay to use 1860 and 1870 as your 2 points, or 1870 and 1880, but I'm going to go ahead and use the 2 points on either side of it. So it's the function f, okay, in the year 1880 minus the function in the year 1860 over the years 1880 minus 1860. I could include the units in my work here, but I'll do that in my next step. So the rate of change in the year 1870, okay, notice how I went to equals. Okay, I'm going to approximate it using this, but the computations themselves can be thought of as equal to. Okay, so I can go from approximate to equals. F of 1880 minus 31.4, and this is millions. And 1880 minus 1860 is 20 years. Okay, I'm going to keep the equals here. Once you simplify, you're going to get 0.94 millions per year. Okay, now let's look at part B. This is part A. Part B says interpret the meaning of the value you found. Well, it's a positive number. Okay, so I think that the population is increasing. If it was a negative number, I'd be saying decreasing. The population is increasing at an approximate, we're using the word approximate, because remember I'm using an average rate of change to approximate an instantaneous rate of change. The population is increasing at an approximate rate of, dump in your answer, 0.94 millions per year in 1870. So remember what we were doing? We were using an average rate of change to approximate an instantaneous rate of change. So, you know, when I go to the interpretation part of it, when you compare these two interpretations here, okay, this is an approximate rate, okay, at a specific time. The time is 1870, as opposed to here when it went over an interval of time. Okay, so we weren't approximating at one moment in time, but instead in example 1, approximate or finding the average rate of change over that time interval. So there's a difference between these two interpretations here. Okay. All right, and that concludes this page. All right, and so the last part in this video, or page in this video, is the instantaneous rate of change, or as we've come to know it, IROC. Okay, the rate of change at a particular moment in time, at a specific location. Here's just the background. You might want to revisit that. Let's look at question number 1. Okay, what is the IROC at 2 of this function? Well, let's find the derivative and evaluate it 2. So the answer is negative 2. All right, let's look at example 2. It says evaluate this limit. What does it represent? Well, this is the limit definition of a derivative, and you can kind of see in here that the function we're dealing with is what we're subtracting. So remember, this is f evaluated at x plus h, and this is f evaluated at x. So this is really just our function right here. Okay, so this is the limit definition of a derivative. We see the structure of it. If this is our function, what does the limit of this difference quotient mean? Well, it represents the instantaneous rate of change of f of x. All right, so if I'm going to evaluate this, sure, I could go through and FOIL that, collect all this, you know, cancel things that can cancel on the top, factor out an h to divide out this h, and then plug in 0. Okay, but that's a lot of work when we already know that this is the limit definition of a derivative. So let's identify the function in here to be this quadratic. So this whole thing, the answer, okay, would be the derivative. So if I did all that work by hand, long ways, I'm going to get this derivative. Okay, so this limit represents f prime of x, or the rate of change of f. And notice I didn't use the word instantaneous. I could have, but in context, if I don't use the word instantaneous, that's what it's implying, instantaneous. Okay, so without the word instantaneous, it still means instantaneous. It doesn't mean average rate of change. All right, so that's the limit definition of derivative. You want to identify the function. If you're asked to find the answer, then you're just going to want to go, hey, I can use my shortcut rules. There's the derivative. Okay, let's look at example 3. Okay, so it's saying which of these 3 choices would correctly represent the limit definition of finding the slope at some particular a value? meaning some specific x. Okay. Now, I think on your note card, let me change this. It's been updated. I just don't have an updated one. I think the only change to this page is that this should be h approaches 0. Okay, if you think about the limit definition of a derivative, okay, we usually see this with an x here and an x here. Okay, and if we had an x here and an x here, then that would mean f prime of x. Okay, but because we have a's in the x's spot, that does represent f prime of a. So number 1 is a correct form of the long way to represent the tangent slope, okay, on f at a. Okay, and this is actually a limit of a difference quotient. Notice that as x approaches a, if x goes to a, your denominator is going to 0, and that's what we want to do, okay, is approach 0 in the denominator. All right, let's look at number 3. It starts out looking like the limit definition of a derivative, but what we want to see is right here, we want to see that x is going to, or sorry, h is going to 0. Well, there is no a in here. X going to a has no meaning. So we're going to say that the answer is 1 and 2, that both these formats would represent the tangent slope at a. All right, so in this video we reviewed the IVT, the AROC, and the IROC.